The motion of an object that is dropped from rest and falls straight down was observed. After constructing a computational model based on the physics principle of Newton's second law, aka the momentum principle, the effect of gravity was observed. The model initially over-predicted the ending position of the falling lion, but after a drag force was added, it was an extremely close model and the final predicted position was off by only 0.00005 meters. The video was recorded at 24 frames per second. The height of my friend was measured to be 1.7 meters, which was used to calibrate the length scales of the video. The coordinate system was used with the origin at the center of the lion's head. The y-axis was aligned so that the object moved in the -y direction as it fell. The video was slightly tilted, so the axis was tilted to reflect this. At each frame, the center of mass of the object was determined by eye. The mass was estimated to be 4.5 grams. The object was blurry at points, but I made the best estimate possible. The computer model uses Newton's second law. The change in the velocity is now non-zero, so that implies that the net force is not zero, so there is some interaction on the object. The first model is representative of simply the weight force on the object. It is initially found at time 0 and location 000. The initial conditions were implemented for the lion as the object. The mass of the lion was approximated to be 4.5 grams. The initial position and velocity were both zero since it is started from rest and the origin is the chosen coordinate system. The time is also t equals 0. It was also made sure that delta t is small enough. The loop is the second law repeated until the ending time of 0.667 seconds. The total time is that of the time in the video. Each equation is updated to reflect the equations V final equals V initial plus F net divided by the mass times delta t. The weight force on the lion was found to be the mass times the gravity times j hat, which is representative of the interaction of the Earth with the model. The observed position of the object was plotted against time. The object fell for a total of 0.667 seconds. When the first model was ran through VPython and was compared to the experimental data, you can see that the final position was over-predicted as shown by the lines. This is due to the fact that the computer program does not account for any other forces. To obtain more accurate results, it is necessary to add a drag force, which is dependent on the properties of the object in question. In order to account for this force, this segment of code was added, shown right here. It is important to account for this drag force in the net force of the system to get accurate real-world results. This force was found to be negative b times the magnitude of the velocity times the velocity. From here, various b's were tested, and the closest drag force was found to be 0.01265. After finding this value, a much more accurate model was seen. You can now see that the new drag model position, shown by blue, is much more accurate than the initial model position shown in orange. It is much closer to the actual experimental position shown in red. The model is predicting can be represented by arrows. These arrows represent the vector forces. The change in the arrows show how the forces on the object behave in real-world observations. This code was made here. The first arrow representing the weight force is constant size and points in the -y direction. The arrow representing the drag force was not yet visible, but is seen and gets longer as time advances. The magnitude of the drag force depends on the speed. This new model is very accurate and predicts the final predicted position almost perfectly to the final observed position. The predictions towards the middle, the model under-predicts the motion. This could be caused by the guessing of the weight and the overall video quality. Terminal velocity is obtained when there is a net force of 0 on an object and there is 0 acceleration. This object does not have 0 acceleration at any point during the fall, so it can be concluded that these models do not predict a terminal velocity. If the object was initially thrown downward, the terminal velocity could potentially change. However, that can only be determined if excess information is determined. Overall, this lab provided a very accurate display of Newton's second law with a non-zero net force.